Um, my name is Prasad Kadambi, and I want to welcome you to American Nuclear Society's Risk-Informed Performance-Based Principles and Policy Committee event. We call it, this committee, we call it RP3C. The purpose of RP3C is to help modernize ANS standards. Modernization has come to mean that risk-informed performance-based methods are employed to overcome the difficulties that we all know about with purely deterministic and prescriptive methods. We've been calling these methods RIPB approaches. There's a lot of guidance available about RIPB approaches, but most people have not had reason to become familiar with the guidance. We've initiated these community of practice webinars to enable practitioners of these approaches to share their knowledge and experience. We had the first of these webinars in February, and we try to have one on the last Friday of every month. We began with a presentation about using a systems engineering framework for enabling RIPB methods. We've had a couple of other seminars. Today, I want to welcome Nilesh Chokshi as the presenter. Nilesh is, I consider at least, one of the world's authorities on seismic safety in nuclear power plants. And I'm looking forward to everybody hearing from him and learning about this subject. So Nilesh, go ahead.
Okay. Good afternoon, and thanks Prasad for that kind words. At least I've been able to fool some people. So as Prasad, I think mentioned, I was with NRC for 34 years. And after my retirement, I returned to NRC part-time as a consultant under the rehired annuitant program. And since then, I've been consulting with NRC and other organizations on the seismic and risk assessment type of programs since even now I'm doing that. The subject I'm going to talk about, there is actually an NRC project underway on this subject. And I'm not going to talk about the project. What I'm going to talk about is general concepts and the subjects at very high level. So in that sense, what I'm going to talk about are my views. There's nothing to do with the project. But at the end, there is a public meeting NRC has organized. So I will do mention about that on the subject, which is, it's already announced and some documents are available. Now, since I mentioned the project, let me tell you that the project is being conducted at Southwest Research Institute under the project management of Dr. Osvaldo Pensado and John Stamatakos and B. Swajit Dasgupta. Bob Budnitz, Ravi Ravindra, and I are also the part of the project team as a consultant. Okay, and I'll give you the information about that NRC public meeting at the end. Can we go to the next slide, Pat? Okay, so as you know that for the advanced non-light water reactors, industry has proposed a framework under the licensing. That one under the licensee modernization project, and which is documented in NEI 1804, and this LMP framework is the risk-informed performance-based framework. NRC has endorsed this framework, and in fact, Regulatory Guide 1.233, which endorses this framework, was published this month. I believe it was June 9th, and it's available on the website. At the same time, in the seismic engineering practice, the use of risk-informed performance-based methods, use of probabilistic methods such as probabilistic hazards, and the conduct of seismic PRAs has been pretty widespread and has been really exercised from late 1970s. So given the availability of and some practice in the civil structural engineering and the seismic engineering, and the new framework for the advanced non-light water reactors, this is a unique opportunity to effect this change and also to move forward with the implementation of the risk-informed performance-based seismic design. And as you will see, as I go forward with what changes we are talking about, but there has always been a constant, particularly a lot of seismic engineers lament that the criteria are very conservative, they should have more freedom. Here is an opportunity. And given the motivation, both from the regulatory side, from the industry side, and the available of technology, I think this is really time to embrace. There is a strong motivation, and there is always a resistance to some change, but I anticipate that this is the time we won't face much resistance. So this is really a time to do this work. Let's go to the next slide. So let's talk a little bit about the licensing modernization project for LMP Framework. As I mentioned, this is a risk-informed performance-based framework. And at heart of this framework is the use of the probabilistic risk assessments to make many major licensing decisions and criteria. For example, the licensing basis events are derived based on the risk assessments and in conjunction with the risk criteria that's shown in the second bullet, the frequency consequence target, which it defines the risk significance criteria. The frequency consequences target, where the consequences are in the terms of the total effective dose equivalent at exclusion boundary and also the cumulative risk. So from the LMP framework, a PRA really becomes a very major part of that regulatory framework. In the LMP framework, the PRAs are supposed to be conducted for all the initiators and all for the plant conditions. And as we go towards these new designs, which are passive and inherently more safer, the external hazard, particularly seismic, becomes an important factor because of its uniqueness, inability to affect the entire plant, both prevention, mitigation, and all system structures and components. Luckily, seismic PRA technology is mature and well practiced and can easily be integrated into that framework. And you will see that how the seismic PRA is going to play a major part in the moving forward in the seismic design. So let's go to the next slide. So this is just shows what the frequency consequences target looks like. I'm not going to spend much time, but the point here is that there is a risk criteria both at the event sequence level and at the cumulative level, which is in terms of the individual risk. And here are the different dose limits or the different regulations. So, and here are the different zones according to the seismic. We are talking about event frequencies in this area. Design bases are generally tends to be 10 to the -4. So this is just to show the concept of that there is explicit risk criteria into the LMP framework. Can we go back for a minute? This previous slide number 3. But I also want to point out this is a risk-informed performance-based criteria. So there are other considerations such as the difference in depth, adequacy evaluation. So it's important to remember that this is risk-informed performance-based criteria. So now let's go to the slide number 5. So the question here is, how do we integrate this framework in applications of structural analysis and designs? So there are 3 things here to think of. One is the total plant risk performance target, which I showed for FC curve, which has a both event sequence risk and also the total plant risk in terms of the cumulative and individual effects. So now you have total plant risk, you have a event sequence plant level targets, and the seismic PRA sequences will also be mapped onto those targets. And now you have to take these targets and convert them to the individual structural system and component design performance targets, so that when you design your component SSCs to their targets, you would satisfy both the event sequence requirements and the total risk. Now, as you can imagine, this is an iterative system. Okay, there is many ways you can do these things, so it's not a unique solution. And it's also inherent in this concept is that you can optimize your individual SSC design so that you can achieve both optimal in terms of the design performance, but also in terms of the cost and safety. So that's an important difference between what we do today and what this approach, at least conceptually, allows you to do that. You can select your individual design performance targets, okay? Just conceptually. So now the basic question is that how do I define my individual performance targets if I were to implement such a process? And once I do that, how do I design my SSCs? Okay. And that's what the whole thing is I'm going to talk about. Okay. So let's go to the next slide. So in order to accomplish that, what I just said, that, how do I go about determining what should be my design targets, and how do I implement it, and how do I implement it in a very near future and for immediate use? Okay, advanced non-advanced reactors are moving forward. I don't think we have a luxury of waiting for 4 or 5 years to develop things which people can't use today. So that's so some of the guiding principle. So we thought about and we can use is that we want to build in the existing risk-informed performance-based approaches in structural seismic engineering. And I'll show you a slide. There is a lot of practice and technology already exists. Something like a nuclear power plant design, and particularly things like structure systems and components, are done by using codes and standards, and it's done by a team of people, sometimes teams consisting of tens of engineers. It has to be done in a very structured manner, and so you want to use existing codes and standards. These are design codes, construction codes. You also, of course, if you proceed, there will be some regulatory framework, or not necessarily regulatory framework, but there might be some need for changing the guidance. But again, the idea is to see that, not to how much you can really accomplish within the current regulatory framework. So the idea is to do something which is very familiar with the design engineers, but it does allow the flexibility of determining the design performance targets and the design processes. Okay, so this is what is driving is to be able to do it in a very quick, and then and given the tools, we can really do that. Okay, let's go to the next slide. Now this slide is very busy, but then I can spend a lot of time, but I'm not going to do that. So as from the point of view from the seismic PRA technology and general use of probabilistic methods in seismic engineering, the use of probability hazard and seismic PRAs and many other like margin studies really gained momentum in late 1970s, and many PRAs were done in the early 80s. Now, based on many insights from those earlier PRAs and margin studies, the Department of Energy had undertaken a development of risk-informed performance-based approaches for its facilities. Now, And that's the top part of this graph presents. And then in the about mid-90s or early 90s, DOE published a standard 1020, which basically defines the criteria for natural phenomena hazards analysis. And these requirements of the standard were established through basically AC 4305 as a technical document. And this is what the document I'm going to talk about a little bit more, because this is where the question of the performance-based design is explicitly addressed and criteria provided. The ANS 2.26 defines the risk criterion for the DOE facilities. Now the DOE facilities converts a full spectrum of nuclear power plant and the facilities where the only hazard is to the occupants. So it's a wide range of facilities, and those facilities in this construct are divided into the 5 groups: SDC 1, 2, 3, 4, 5, SDC 5 being nuclear power plants.
Nilesh, are you on a different slide than is appearing there?
No, I'm going to come to that more, but this is, I just want to mention what the DO. So what the point of here is that there is also, a risk-informed performance-based framework exists in this framework when the DO, since beginning in the 90s, okay? If you look at in the NRC land, the use of probabilistic hazard and the introduction of probabilistic methods in the 1996 revision of the siting criteria and the publication of REGAD 1.208, which uses performance-based approach for selecting seismic earthquake ground motion. And then for advanced reactors under Part 52, there is a requirement for doing seismic PRA or margin analysis. The point of all this is to say that quite a bit of tools and infrastructure exists, and we can utilize that. Let's go to the next slide. Okay, so I'm going to talk about AAC 43, okay? And as the title suggests, it's a seismic design criteria for structure systems and components in nuclear facilities, and it covers facilities besides nuclear power plants, okay? And when it was originally promulgated, it was a standard for a design of new nuclear facility using performance targets for individual SSCs. And I'll be talking about this. The second bullet, I won't go in detail, but there is a quantitative performance targets exist in this standard in terms of unacceptable performance. Let's go back to the same slide, okay. Yeah. Okay. And then so now I'll say a little bit more about that. But as you see that there is a specific target in terms of probability of accidents or in this standard. Let's go to the next one. Number 9. Yeah. Okay. Now here I'm going to spend a little bit more time because this is the crux of the what I'm going to talk about. So in AC 43, there are 3 basic things. Okay, one is once you know what is the and I'll come back to that how you select SDC. But for a given seismic design category, you select based on the performance target requirement. You select the design basis earthquake return period consistent with that category. And so you are already introducing the concept of how to design basis earthquake and how it matches with the performance target. The second parameter, which is very, very important, is what should I design my structure to in terms of performance? So currently, for example, we design a structure to elastic limits or allowable stretches. The question is, do I always have to design to that very strict criteria of remaining elastic that I can still let my structure yield and go into non-elastic, but that's an adequate design requirements. Now, the So that's the option is provided into the standard. So there are two basic important parameters. How do I define my design basis earthquake, what return period, and what should be my limit state for the design. Now the limit state, you have to be, this is an important point I need to understand. The design limit state is not the functional, ultimate safety functional limit state or the fragility that you use in the risk assessment. So there is still a significant margin beyond the what you design to as traditional design process, when you use codes and standards. And that's very important. So to give you an example that if I have a structural wall and I can let it deform to a great extent and still it does my safety function, for example, supporting a safety related component or something like that, then I can let it be designed not to a very strict elastic limit, but I can also relax my design requirement. That is the notion we are working on, okay? Right now, in the current approach, there is only one design basis earthquake, which is selected, which is applied to all safety related equipment. And all safety related equipments are designed to basically prescribed limit states, and in some cases they tend to be conservative. And this is the message in this blue box, okay? So this approach, because of ability to select the return period of the design basis earthquake and the ability to define what should be the design performance, allows you to control your safety margins and conservatism in accordance with the risk significance. That is the biggest change now this process will implement. And as I said, in the current approach, all safety related SSCs are designed to same design basis earthquake and prescribed conservative limit states. And in the ASCE 43 language, and you will see in the next slide, it will become a little bit more clear in the next slide. The current approach is equivalent to seismic design category 5 and limit state D, okay? So this is the most important, this is the difference between what currently being done and what this new approach would allow. Let's go to the next slide. So in this slide, there are three SDC categories they've shown, 3, 4, and 5. I mentioned that nuclear power plant 5, the target performance goal is 1 × 10⁻⁵. What that means is that if I design individual SSCs according to in category with the SDC 5, the annual probability of exceeding design performance, the mean probability is 1 × 10⁻⁵, okay? My design basis earthquake is derived using a return period of 1 × 10⁻⁴, which will, if I do this, if I use this design basis earthquake and the design procedure outlined in ASCE 43 and companion standards, I will achieve this target performance goal, okay? As you see that if you go to the other categories, this target performance goal becomes larger, but the design basis also becomes smaller. And then the codes and standard you use also will vary to some extent. So this is the major concept, one of the major concepts in the ASCE 43. Let's go to the next slide. The limit states. So in the ASCE 43 construct and ANS 2.26, there are 4 limit states defined, okay? The limit state D, essentially elastic behavior, basically there is no damage, and this is what is being currently used for the safety related design, safety related SSCs. C would permit limited permanent distortion, but minimal damage. And A and B, which are much more liberal, you remember the DOE facilities as a full spectrum. For nuclear power plant, we probably talking about C and D, okay? So again, repeating 2 basic concepts. what should be the numerical performance target, what is the design basis, what is the design process, and what is the limit state I'm going to choose. Those are the four fundamental things in the thing. Okay, let's go to the next slide. Okay, before I go to the next slide, these are the building blocks. Okay, the LMP framework and AC43 construct are the two basic concepts, and the next thing is how to combine these concepts into a potential process which fits into the LMP framework and also utilizes the AC43 tools and other codes and standards. So before I do that, any questions so far?
I have a question. Oh, go ahead.
I'll wait.
My question relates to, well, first of all, I'm, as you know, very supportive of this approach, and I'm sure Bob Kennedy is smiling down upon you at the moment. But my question relates to then, what are the implications for something like an OBE? Because it makes it a lot more, I remember I used to explain, like in public meetings, the concept of an OBE being an acceptable value, because you could always say, well, if we're designing to linear at the SSE, then certainly.
Yeah, I think that's a very good question. And I did mention that NRC project, and I'm going to, in the end, talk about one of the reports where we have discussed, some of the regulatory considerations. And in terms when you're selecting certain things about design, how do you take into account things like OBE, okay? And I mentioned that there are some minor guidance changes and things. And those are the areas where you have to think about a little bit more. I don't think I can go in detail how you can handle that question, particular OBE. There are few other questions like that. But we discussed that in that report, which I'll talk about a little bit. Okay, and that's what the NRC project is about, is to look at from the broader perspective, from the regulatory perspective, what, in implementing this kind of approach, what things you have to think about. There are a few other items like that. It's a good question. And definitely you have to think about that. And I think if I answer that question in detail, I will probably bore a lot of other people.
There was one other question, I think.
I will wait to the end. Thank you so much.
Okay. Go ahead, Nilesh.
Okay, so let's go to the one slide before this. Okay. No, I mean, earlier slide. Okay, so this is okay, so what this, I think the process we are developing, which exploring the possibility of assigning alternate design basis earthquakes and limit states to structure systems and components according to their risk significance. Once you determine that thing, the design process is becoming very familiar process using the current codes and standards. So as an example, and I've shown here what a potential process looked like. And I mentioned the PRA becomes a really major part of this process. So you basically, if I go through very quickly, you start the initial process by selecting some initial SDC and LS categories, and most likely you will do the way we do today, SDC5 and limit state D. You perform a seismic PRA, and identify the major, I should have event sequences, okay? As I showed that a frequency on the FC curve. You look at, so that way, then you can compare those things that you can display the results in terms of those frequency and consequences on the FC plots. And then you can determine which are the importance of each SSC, okay? Now, if you also recall that the LMP also has an SSC classification. But anyway, on this, by going through this process and looking at the risk results, you can determine what risk significance of each SSC is, okay? Then you can change your SDC, the SDC category and LS categories, and then repeat the process. One important thing is in making those decisions of revising and going to say lesser categories, is to remember that this is a risk-informed process and there are other considerations such as defense in depth and other things come into play in making those determinations. Then you again, you can revise your seismic PRA and you can iterate to optimize your selection of SDC and LS for different structure systems and components. I want to add one thing and not want to give a wrong impression. You would not do these SSC for every structure systems and components. Generally, it's done. It could be in a practical settings. It will be done based on groupings, and we already have some experience with doing that kind of things in the light water reactors through 50.69 process, where we have grouped SSCs in a different risk categories. So the idea is to merge the PRA technology, the LMP risk criteria, and the ability to choose within the different categories based on ASC 43 construct. And that's what a process would look like conceptually. So this is what the NRC project is exploring a lot more in detail how to go about doing this. So let me go to the next slide. So this is, okay. So in summary, I think that one of the biggest benefit of this is the allowing designer a flexibility, okay? In the flexibility in terms of what design basis to select and what design limits according to risk and safety significance. Flexibility, I think in my mind is that today you may not think about all the potential benefits and also in some difficulties you can think of, but flexibility allows a lot more than just the flexibility in design. In the past, once something was determined safety related, you did not have any flexibility. If you knew that you had a flexibility, you might start thinking about that question right from the basic layout of a design, okay? We know the problems with the construction conditions of reinforcement and things. So even if you can reduce a little bit of reinforcement because of this approach, you may not be able to appreciate that flexibility now, but during the construction. So I think that's the biggest benefit. That's what my point is, that the flexibility to some extent tied to a performance and the risk goals is really opens up the door for many other things. As I mentioned, efforts are underway to establish links among that doing this, and that is being right now done under this NRC project. And okay, the next two bullets are obvious. So that's sort of the end of my presentation, and the next slide is the little information on the NRC meeting. So let's go there, and then I can take questions. So the meeting is on September 2nd and 3rd, and if you go to NRC public website and look at the meeting calendars, click on September 2, and you will find the information. Along with the announcement, there are 4 documents. And the document number 2 is the draft report, Southwest Research draft report on the proposed methodology, okay? And so that has a lot more detail than, in terms of, any sort of also includes discussion of OBE type of question and some other things you have to think about, okay? But this is all publicly available, and if you can get it, there are ML numbers here. Okay, so with that, this is the end of my presentation, and if there are any questions, hopefully.
There was one question, but before we get to the question, I just want to add that Nilesh spoke about the LMP, activity, and he did not mention, I don't think, the report itself. It is NEI 1804, and NEI 1804 was reviewed and accepted by the NRC in Regulatory Guide 1.233. So just want to make sure that people understand we are talking about, for a lot of people, these are familiar numbers, but maybe not for everybody. So. Let's see, there was a question there. Not
Yes.
sure.
Yes.
Go ahead. Go ahead.
My name is Farzin Zavorian. This is the first time that I'm attending one of these talks. I have to say that I really enjoyed it. Thank you very much for giving it such a nice talk. I'm not doing anything related to the nuclear world, but I'm very much familiar with the process for building and bridge. I don't know if any of my colleagues in that area are on this call, so if they are, I'm going to say hi to them. I have a few questions about the process. One of them was, you mentioned about the sequence of events. This is the hazard of the ground motion, right?
Let me make sure that I understand the question. When I talk about event sequences, in terms of, I'm talking about something like what happens a certain initiating event occurs, the earthquake occurs, okay?
Sure.
And what happens to the facility, okay? How the plant functions work, and what is the end state, whether it results into some kind of accident like damage to the core, or whether it survives, okay?
Sure. No, what I mean is it was something on the vertical axis, which later on you showed that based on ASCE 43, if I remember the number correctly, it goes to 110 to the -5. I think that's the annual rate of the event that you're designing for.
Okay, let's go. I see what you said. Okay, I think that's a slide number 10 or 11, I think.
Well, actually, it was on the earlier part. This was slide number 3, I guess, or 4, the one that you have a chart. Yes.
Oh, this one. Okay.
Slide 4, yes.
Okay, yeah. Okay. Right. Okay. Can you, that FC target? Okay. Okay.
Yeah.
Further, this one, this yellow, right? Yep,
Yeah.
that's one. Right.
I mean, the vertical axis is the annual rate.
Yeah, it's event sequence frequency. Okay, so look, for example, what is the frequency of an earthquake to occur, in a plant year? Okay.
Yeah.
So
like
that, okay.
One every 10,000 years.
Right. So let's say that, in a nuclear power plant risk assessment, you look at the entire seismic hazard, okay, from the low level to the high level, okay.
Mm-hmm.
So the earthquake event that occurs with a more frequent and less frequent, the events which we are interested in and where we do the design are this area, okay. The one in 10,000, and that range. So that's the event frequency, okay? Event sequence frequency.
I hear you. Now the question is this, and again, this is from my lack of knowledge about how the world has changed in the nuclear area, because the things that is happening right now in building and bridges is the information that you mentioned about that the nuclear world created in the 70s. The work that Ellingwood and Cornell started by probabilistic seismic hazard analysis. That is what's happening in the building and bridge world right now.
Right.
So coming to the question, if we're looking into a return periods of every 10,000 years, there are other events that are happening until the time that we reach to that major event of a 10,000 years. Do the models incorporate the cumulative damage that the power plant might be seeing? Or are we going to look into foreshock, shock, aftershocks? Or we are only focusing on the main event that is going to happen every with the average return period of, let's say, 1 every 10,000 years?
So there are, I think there are two. So in the design, okay, you design to a big event like 1 in 10,000 or something, okay. Mm-hmm. But when you do a risk assessment, you look at the events of all sizes. You look at the full from a low level of seismic, say earthquake acceleration, to the high levels in up to 2G or something, okay?
Mhm.
So you look at the full spectrum of hazard when you compute the risk, okay? You look at the on the plant impact of all different motions. And in generally, the low earthquake, they don't cause that damage because these plants are designed to very light earthquake. But you do look at that, okay?
That's your key. So you can take it back.
I think that out of time, I have a few other questions. I think that the talk was scheduled for 30 minutes. I will probably contact you offline that I can ask my other questions.
Yeah, I think some of this require probably more detailed discussion, you know, and right, yeah.
But it was a very nice talk. Thank you so much for presenting.
Thank you. Yeah.
Thank you.
Nilesh,
There's one other thing I'd like to just mention, if I may. You know, the approach that Nilesh has described has been thought to be applicable in a generalized way to external hazards in general. So, you know, it can be applied to other kinds of hazard, whether it's wind or you know, other kinds of hazards. I don't know if you want to say anything about that, Nilesh. So.
Yeah, yeah, I mean, in principle, conceptually, it is, you know, but the maturity of technology is in a different places. So you have to do according to what the technology is available. But yeah, conceptually, there is no impediment not to do this kind of analysis.
Nilesh.
Yes.
Antonio Godoy, just two questions. The first question, using the opportunity, you have this slide number 4, the performance target, the global performance target of 10 to the minus 5 as established in relation to the equivalent dose correspond to what we call PSA level 1. That means core damage frequency.
So remember,
to level 3, which is the impact in the individual or collective dose after dispersion. I mean,
right.
After the containment fail, and then dispersion, and then going to the public or to the, therefore this is level 3. I understand that that's a question. I understand that this target performance corresponds to PSA level 1. That means core damage frequency. Is correct?
No. And actually, I think there are people in the audience who can explain this much more. But remember, this is not non-light water reactors. Yes. So the concept of core damage and traditional accidents we think about not necessarily apply here. So these are strictly in the limits of dose. Okay, so it does dose at exclusion boundary. So it is, if you say, it's more like level 3.
Is more at level 3.
Right, because you are computing the effective dose equivalent.
Okay. The second question, Nilesh, is regarding the SSC classification that you pointed out in one of the slides, I think.
Right.
And then in the slide number 12, you put that for new design, there will be some changes in the classification in order to consider more the actual importance. Right. My question is, do you expect a change in the way or the criteria for which we define category 1, category 2, category 3, etc., non-categorized item in the classification?
Yeah, what I see that once in that LMP framework, there is a classification of they define SSCs, but from the seismic design point of view, for example, we could have something like a containment structure. You will still design to the elastic limit, the most conservative criteria, SDC5 limit state D. But you might have other buildings or other components that from the risk perspective, you don't need to design to those conservative criteria. So there may be safety related or the, the safety related but special treatment in according to LMP classification, but they would have a design, seismic design category SDC4, limit state C, okay? So it will be more than one single safety related seismic category 1.
Okay, thanks.
Because yeah, I mean, you are right. I mean, depending on risk significance, you will be able to do that. And that was the whole idea, that you don't design everything to the SDC5 limit state D.
Thank you.
Hey, let's see. I just want to mention, unless there are other questions, this presentation of Nilesh and the other presentations from the community of practice events previously held are available on the ANS website at the RP3C page, RP3C page. So if there are any questions at all, please don't hesitate to get in touch with me. And, I'm looking for input on other such events. So if anybody has been working or is working in an area there you think can be used as one of these presentations, I would appreciate your coming forward. Or if you have suggestions on, what type of presentations you'd like to see, I would appreciate all that input. So if there are no other questions, I want to thank everybody for participating. I hope it was useful to you, and we would appreciate any feedback that you have to offer. Pat, do you want to close out?
Can I ask a question to Nilesh?
Yeah, sure, please.
Because there is some, Antonio again, because it's first was very, very interesting, the presentation. I think I enjoy a lot, and there is a lot of information on that. But I would like to know, as an engineer that has designed deterministically, seismically designed in a deterministic way to nuclear power plant when I was young, if I should do the same now, using this probabilistic design criteria. It was clear to me what will be the main changes, particularly in one of the last slides when you pointed to the global performance target and to the design limit. You said something about the concrete and the reinforcement. My question, Nilesh, what do you expect if you apply this approach instead of the old methodology that we applied 40 years ago? Okay. What do you expect?
So that's a good question, and I think I'm glad you asked, because there should be, once you determine the design basis earthquake, okay, and once so for example, SDC5 or SDC4, I determine what should be my design basis, and I design whether I want to have for a structure, say, elastic limit, or I want to permit certain inelasticity. Okay, those are the two critical decisions are made based on this process. Once that decisions are made, then design is carried out accordingly how we carry out design. That part doesn't change that much. So for example, if you go into AC43, okay, if I'm designing to the SDC5 and limit state D, it will look just like the way I do today. If I go to the limit state C, which is inelastic, in AC43, it tells you how do I change my required loads because of the ductile, because of the deformation. So there is same process. You go through the process of codes. So that part is very much remains, Antonio, that's how you and I used to do the designs.
Okay. Yeah. Also, Nilesh, because the dimension of the structural elements, at least in reactor building, are imposed by layout and radiation protection. And then the reinforced is mainly main structure fixed by the minimum amount of rebars.
Right.
Therefore,
Well, in some cases, right? I think if you, this may not be a good example, but if you know about several containments, that the questions of the voids and the constructability because of the congestion of the steel, particularly when you have a lot of diagonal steel because of the seismic design.
Right.
Okay.
Right.
Now the second thing, I think, important thing is that even if you, like, let's say, for example, I let my seismic category 1 building, I can let it deform a little bit. I get a permit in elastic deformation, okay? That reduces the seismic load to the everything, to my equipment, to my piping systems and everything. So you're reducing, say, even by 15-20%, it permeates through the entire plant. Okay.
I agree fully with that.
So that's, these are the kind of questions this NRC project trying to exploring to get a better handle. And as you said, that in nuclear power plant, at least in the light water reactor, seismic design, like thicknesses of outside wall and things like that are covered, generally governed by a lot of other factors also, tornado design, pressure loads, right?
Yeah.
But so you have to think where you can take advantage of, or where it's possible to do this relaxation.
Yeah.
But there are many opportunities, like that's why I said containment is a bad example, because it's the criteria is leak tightness. You're not going to permit inelastic deformation. but so this is but having that ability for a designer to make those decisions, that is important. And particularly in this passive, the advanced light water reactors, where you're talking about much fewer components and low risk, you can examine this question much better. Light water reactors, it's a complicated system, but probably also there is more opportunities because there are so many components which are affected. So. Yeah, these are good questions, and these are the practical implementation questions which we've been trying to look into this NRC project.
Thank you very much, Nilesh.
Let's see, I just want to add that when it comes to containment, one of the changes that has occurred and is available for non-light water reactors is this idea of functional containment. That can create a whole series of advantages relative to flexibility, how that is applied to functional containment is part of, I think, some future study has to undertake.
Right, and I think that is the thing, this flexibility can lead you many places.
Okay, thank you all. Appreciate your participation and questions. And Nilesh, I want to thank you, and we'll try to keep these things going. Any suggestions from people are appreciated. Pat?
Yeah.
Yes. Thank you all very much.
Yeah.
I'll go ahead and end this webinar, and as Prasad said, it will be posted on RP3C's website. It's a public site. If anyone has any questions of how to find anything, please go ahead and email me. If for some reason you're not sure of my email, I have a generic mailbox as well. It's the word standards, plural, @ans.org. Thank you all.
Thanks.
Bye.
Thank you, Prasad, for the opportunity, and Pat.
You're always welcome.
Thank you. Bye.
Thanks. Bye.